Welcome everybody in the lecture hall on Zoom from the future. Today we are going to continue the coverage of Tolerant Retrieval, which is about spell checking, about how to query data when the query isn't quite correct. There might be characters that are not the same as in the document, so spelling mistakes. If time permits, we'll also look into the index construction, so how to build the standard inverted index when we have more scales, right? All right. So just so you know, Marco, you need to admit as people arrive. You just need to click on admit all, and then the people can be admitted into the Zoom room. All right. So as always, I will start with a few questions to ask via the Clicker app, and then you can test your knowledge of the previous weeks, and then we will continue taking it from there. So here is the first question to you. These are trees, whatever they are, and some of them are 3-5B plus trees, and some others are not. So I'm asking you to let me know which ones, multiple answers possibles, are 3-5B plus trees and which ones are not. So I'm going to display two at a time. So I'm showing you the first two right now. Maybe you see them on the phones, but it might be a bit small. So then I'll scroll down to show you the other two. So you can already look at these two. So these are the first two. I'm going to scroll down to the other two. These are the other two. So we are looking for 3-5B plus trees. According to the convention that I showed you last week, right? Because I warned you that there might be multiple conventions in use across the world. All right, these are again the first two. Let me see what answers you gave. So a lot of votes for the first one, or 3-5B plus trees, some votes for the second one, and no vote for the third one, some votes for the last one. So let me show you the answers. So the second one is indeed a 3-5B plus tree. The other two are not. So let's look in details. Let's start with the easy ones, maybe. So who can tell me why the first one right here on the top is not a 3-5B plus tree? It's a B tree, exactly. Why is that a B tree? Oh, the mic is not working? Oh. I don't know what's happening today in the lecture hall, but things seems to be a bit... Okay, let me just repeat what you just said. So you basically said it's a B tree, not a B plus tree. And why is that a B tree? Yep. Exactly. So it's based on the colors. So already based on the colors, you can see that the everything is colored in the same way, which indicates that the posting lists are everywhere, and that's a B tree, not a B plus tree. You could also see with the numbers that basically you have numbers that appear not at the leaves but in the middle. So that's another indication that it's a B tree. So indeed, that's not a B plus tree. Why is the second one not a 3-5B plus tree? This one has yellow, light yellow for the intermediate non-terminal nodes, right? So why is that not a 3-5B plus tree? You can answer on Zoom as well, if you want. The second one on the screen. Yes? Yes, they're not all on the same level, exactly. A requirement of B trees and B plus trees is that all of the leaves must be at the same level. And here you clearly see it's not the case, right? Because this is at the depth of 1 and this is at the depth of 2, right? So this is why it's not a 3-5 B plus tree. More difficult. Why is the first one not a 3-5 B plus tree? So of course, yes, there is a problem with the 2, 22, and so on. So already for that, you could argue it's not, but it's a typo. Even if it were 22, it would still not be a B plus tree, 3-5 B plus tree. Why not? It's more subtle. Because here there's 1, 2, 3, 4, 5 children, right, for the roots. So it seems that things are okay, right? But there is one thing that makes it not a 3-5 B plus tree. What does this 3-5 mean? What is 3-5? It's an interval for the number of, yes, go ahead. Exactly, and what's the interval for the number of keys on each node? 2, 4, exactly, between 2 and 4, right? So you see here, it's 5, but it should be between 2 and 4. Why? Look at the number of children it would have had if it were an intermediate node. You would have 1 here, 2, 3, 4, 5, 6. It would be virtually 6 children nodes. So that's not okay. So it's the intervals that I told you about. If you have 5 children, that's 4 values in the middle. And that interval on the values also applies to the leaves, right? So the leaves can have between 2 and 4 values in a 3-5 B plus tree. For whom is that clear? All right, very good. And this one is absolutely a 3-5 B plus tree. You can control, right? So 3 here, and it's all between 2 and 4 for the node. So virtually between 3 and 5 non-existing children. The root only has 2. 2 is less than 3. But it's okay because it's the root, right? So the root can have less, and that's fine. So it has 2 children, that's always allowed. Okay, so you did well on that one. Here's a tough one. Now testing your understanding that we've discussed things. It's fine to use a calculator or the internet or ChatGPT. How many terms? I'm wondering actually if ChatGPT could actually answer that, but maybe it wouldn't know our convention. But how many terms or types, so the values, can a 4-7 B plus tree of depth 3 contain at most, right? So it means between 4 and 7 children. Which means between 3 and 6 values or keys, depending on, you can actually call them keys or values depending on the context, but basically the terms that you have on each node between 3 and 6. Considering that the root can have less than 4 children. How many terms at most can a 4-7 B plus tree of depth 3 contain? Regarding the convention, I consider depth 0 if there's only 1 root with no children, depth 1 if there is the root and then children that are directly the leaves, and so on, right? So how many terms can you support in a 4-7 B plus tree? You know what? I know why it's not working. I think I just didn't switch it on. All right, so we have 1512, 2058, 2401, and 1296. We have a majority. And the correct answer is 2058. You are correct. Can anybody tell us? ChatGPT says 6. Okay, interesting. ChatGPT says 6. Okay. So can anybody tell us how you computed 2058? What did you multiply? Yes, go ahead. Maybe I can now that this is working. Oh, almost.
So the root has can have up to 7 children. Each of those can have 7 children again. That can again have 7 children. That can again have 7 children, and those children each can have up to 6 nodes.
Yes.
So we multiply 7 to the power of 3 times 6.
Yes, so 7 times 7 times 7 times 6. Exactly. Yeah, that's exactly it. Right? So this is how you compute the oh, well. Well, that's okay because it's exactly made in such a way that it can fall. All right. So thank you very much. That's the correct answer. And here, what is the most accurate definition of a type? Remember, we talked about types. It's an equivalence class of postings. If 2 postings have the same document ID, then they appear jointly in the index, or it's the resulting set of a query expansion used to query the index, or it's an equivalence class of documents. This induces an equivalence class on the tokens as well, called postings. Or is it an equivalence class of tokens, similar semantically? Types then appear as terms associated with posting lists in the standard inverted index. So what is a type? Is the quality fine on Zoom, audio and video with the Wi-Fi? Okay, thanks. All right. We have a majority. So, okay, so that was rather an easy question. And this is indeed, 100%. Wow, you did well. So it is indeed an equivalence class of tokens. So first you group the tokens can appear multiple times in the original documents, but it's not only that, it's that you also group together, for example, computer, computing, computed, and so on and so on. So it's when you do these sort of things, you have these equivalence classes, and each one of these equivalence classes actually ends up in the standard inverted index, right? The word term is really used in the standard inverted index, right? So every key in your B+3 or everything that has a postings list is called a term in the end, right? So the type becomes a term, if you will, in the standard inverted index. And the tokens, that's used for the original documents. That's when you find an occurrence of a term or a type in the original documents. All right, let's move back to the slides. I think I asked enough questions for now. All right, so you remember the standard inverted index. I already introduced it to you so many times that by now you know how that works. You have terms on the left, then you have for every term a document frequency, this little purple number, and then you have a list of sorted integers. These are the document IDs. That's called the postings list. Every one of these postings is actually a pair of document and term, but you only see the document ID because the term is implicit from the left, right? And then we saw last week that the terms, they are just not a flat list. They are actually organized as a hash table or as a B+3 in order to accelerate either in O of 1 or in O of log. What letter do I use for terms? I think we will use the letter M later. So O of M or O of log M if we want to find a term, or O of 1 if we use a hash table. Okay. And then last week, we introduced something new, the support for wildcard queries, where you can use this joker symbol in the middle. This is not a regex, right? It's not to be confused with the clean star of the regex. Here, it's really just a joker for whatever characters. And we saw that if it's at the end, then that's easy. You can just do a prefix search, in other words, a range query on the B+3, and then you can find out all of the terms that start with these letters, and then find the documents. Then we saw that if the wildcard is at the beginning, then you need more work. You actually need some reverse standard inverted index in the sense that you inverse all the words end to the beginning instead of beginning to end. So you need to add an additional standard inverted index, an additional structure, an additional B+3 that sorts the terms but from the end instead of from the beginning alphabetically. So that takes care of the wildcard at the end. And then we saw that in the case of the wildcard in the middle, there is a trick that's called the permuterm index. Brilliant people who thought about that, which is the idea that you rotate every word, you rotate it in all possible combinations. So imagine putting the letters on a ring with an additional dollar to say where it starts and ends. And then you have all the possible rotations. And you build then some B+3 on every rotation of every term, right? And then you can use the B+3 structure in order to search for a specific rotation. And once you are at the leaf, the rotation points back to the original word, right? So if you have, for example, $ET, it points back to ETH. If you have $PL, it points back to plants, right? So this is how, starting right in the middle of a word, having a wildcard in the middle of a word, you rotate the wildcard query to put back the wildcard at the end, adding the dollar, and then you look it up in here, and then you find the words. And then as a second step, you use these terms in the standard inverted index to look for the documents. For whom is that clear? That we did last week, right? So brilliant trick with these rotations. All right, so it's not the last time we'll see these dollar signs because they will come back today in what is called k-grams. What is a k-gram? Well, imagine this query right here, where we are looking for all the terms that contain MPU in the middle with whatever before it and whatever after it. What is a word? An example of words that matches that? Yes, computer, exactly. So computer. So how do we solve this? Well, we could do it with rotations, right? We could try with the MPU prefix looking in rotations, but there is another way. The trick is to build the k-grams of a word. So what do I mean with that? These are the 1 grams. These are actually the letters. So the 1 grams, the letters in computer are COMPUTER, but also the dollar. We put a dollar at the beginning and at the end of the word. So the dollar technically is also a 1 gram. There is zero information in there actually, because what does the dollar tell us? It just tells us that the word begins somewhere and ends somewhere, right? So this is not very useful here, but you will immediately understand why the dollar when I show you the 2 grams. Because what are the 2 grams of the word? So forget about the dollar for a moment. It's a sliding window over the word. So you have CO, then OM, then MP, then PU, then UT, then TE, then ER, right? So you have this sliding window. But what do we do at the beginning and at the end? We have this $C that tells us, okay, that starts with a C and then R dollar, which tells us that ends with an R, right? So we also had this dollar. So what you do is you write dollar computer dollar, and then you do your sliding window of length 2. Then you have the 3 grams that are a sliding window of length 3. So $CO, COM, OMP, MPU, PUT, UTE, TER, and ER dollar. And then, you basically see how that generalizes, right? Now we've seen that before. Remember, in the byword index, but we were not doing this with letters, we were doing this with words. We had a sliding window of 2 words, and we were looking at every pair of words that are one after the other in the original document. These were actually byword or two-word indices. And I told you there can also be three-word indices, quadri-word indices, or 4-word indices, 5-word, and so on. Well, here it's the same thing, but finer granularity at the letter level, and we call them k-grams, right? So 1 gram, 2 gram, 3 gram, and so on and so on. It's the same principle at the letters. For whom is that clear? All right, that should be easy. Okay. Now, in terms of how useful this is, well, as you might have guessed, the 1 gram is not very useful. It's more a theoretical corner case that we love in mathematics, of course, to still study. But the usable zone is 2 gram, 3 gram, 4 gram. This is actually the usable zone. The 5+ grams, as you might imagine, it's going to explode in space, right? This is going to just consume insane amounts of space. So this is maybe not something that that we are going to do. We do it now actually at the word level, like 5 words, 6 words, 7 words. In fact, that's ChatGPT, right? When you do that, and this is why it's called a large language model. But we'll come back on language models at the end of the semester, right? So I'm not going to talk about that here. We just have the letters. Okay. So what does it mean for us? It means that if we take 2 words, computer and Tolerant, for example, and we build the 3 grams of these 2 words like this, of course, we need to eliminate duplicates if they are duplicates. It might be that you have twice the same 3 gram in there. So we eliminate duplicates. And then we can build yet another index. Now it's going to be called the k-gram index, right? Where you have the k-grams that are the values of our b+3. And then you build, as usual, the b+3 on top of that using these intermediate nodes, right? It's just a b+3. Now we have a lot of them, right? We have the b+3 on the terms of the index. We have the reverse one, sorting from the end of the words. We have the permuterm index, b+3. We have the k-gram b+3s, right? So it starts to be, and we have the k-words b+3s as well. So that's a lot of indices. All right, so now we can look up, and here I, of course, point back to the words that have the k-grams. You see it can have every k-gram here, every 3 gram can have 1 word, like MPU has computer, but you also have some TER that have 2, computer and Tolerant, right? So now, if I consider a query like this, star com star, right? Then I just look up the k-grams in there, so COM, obviously, and I find it going down in logarithmic time the b+3, and I find computer, and then I can actually find it, right? And now, if I have a different query, co-star TER, then I need to look for the k-gram $CO. Why the dollar? Because there's no star at the beginning, so it really starts with C and O, so this is captured by $CO, and then TER and ER dollar, right? So if we look, oh, I didn't put ER dollar for some reason. Okay, you could also add ER dollar in there. But anyway, even with $CO and TER, we already find computer, and that is common to the two, right? You do the intersection. So here, this is how you actually find computer as a match in there. For whom does that make sense? Right? Just look the k-grams in the query, look them up, and do the intersection, compute the intersection of the corresponding term sets. Okay. All right. Now that we have the k-grams, they can be useful for the wildcard queries, very useful, but they can also be useful for spell checks. Because when you have spell checks, you probably notice that if you type this in a search engine, you're going to get these "did you mean" magic words, right? Did you mean this? So you can try to type computer without an O, like CMPUTER. It's very likely you're going to get a "did you mean." In fact, it might not only do the "did you mean," it might, in fact, directly query for the corrected terms. It might not even ask you. It can still give you the opportunity to insist on keeping the mistake, but you can always query for it. Or you can only query if the corrected terms are not in the dictionary, because maybe it's not a spelling mistake, it's just a word that exists, but that is very close to a popular word. Or you can be super conservative and only query if there would not be enough results. In fact, this is typically what's going to happen. If I think it even tells you on Google, there are not many results for this query, so we queried for that instead. And that's actually made with what we are about to see now. And then you can also make a spelling suggestion, so not actually fix it, but just suggest to fix it, right? So you still execute the original query, but the user has an opportunity to click to take the spelling suggestion. Now, how do we do this? Well, there are different approaches, so we are going to look at a few of them. One of them that is kind of the textbook approach is called the edit distance, or the Levenstein distance. Who heard about this distance? Right, you might have seen it already as in other courses. So the idea of the edit distance is you take 2 words, one that might be the correct word and the other one that is the misspelled word, and you want to see how close they are. What do we mean with that? We mean how many edits, atomic edits, would you need, right? So in that example, for example, between or and to, I just took these very small words. You could go from here to here by removing the R. So you have or, you remove the R, and then you add a T. That's 2 steps, right? You need 2 steps. Or you could have 2 steps that you replace O with T and you replace R with O. One step is either inserting a character or deleting a character or replacing a character with another one. These are the 3 ways you can edit a word. And so the edit distance, the minimum edit distance, is the minimal number of steps that you need to apply to a word in order to obtain the other words. So there might be very long lists of edits that are not efficient, but one of them is optimal, and we want to look for it. This, in fact, gives us a distance between words. That's called the Levenshtein distance. All right. Now, how do you do it? Very, very naively. Very naively. Let's try to enumerate all of the possible ways that we can edit this. So, for example, I could have done as a first step, for example, adding O. So if I add O in order to obtain 2, then I bring myself back to the known problem, the simpler problem of going from OR to just T, right? And if I know how to go from OR to just T, then I just need to add O as an extra step, right? Alternatively, I could remove R, right? So from OR to 2, I could remove R from O, and then I'm back to a different problem, which is how do I go from O to 2? Or I could say I'm replacing R with O. So here, this is just this S/something/something. It's a popular way of expressing a replacement string with the sed editor. Who knows the sed editor? Can be very, you don't know the sed editor? Who already saw this S/ notation? Okay, so let me tell you. In fact, it used to work on Skype. When you were talking on Skype and you made a mistake, you could write S/ what you want to correct / what you want to put instead / and it would automatically correct. The sed editor is a bit of a grep editor enhanced with editing capabilities. So grep is going to just look for specific patterns or regular expressions. Sed is going to look for specific patterns or regular expressions and replace the found patterns, right? It's very, very handy also when you write code. If you want to edit 1,000 files at the same time and modify the same thing, it can be very handy. And S/something/something is basically the shortcut that is used in order to do to encode these replacements. So what is meant here is we replace R with O. So if I replace R with O, then I'm back to the problem of going from O to T, right? If I know how to go from O to T, then I can replace R with O, and I know how to do from O to 2. For whom is that clear? Right. And then I just go all the way with every possibility or way that I could have my edits, right? And then at some point I arrive at the problem of going from the empty world to the empty world, right? Of course, I didn't consider it. You could also argue that you add letters that you immediately remove and so on, but that we forget because that's not efficient, right? Why would you add letters that you immediately remove after that, right? So this is a full search space. The name for that is search space. It's the space of all possible chains of edits that go from one word to the other. The problem, and that's common to many search spaces, is that this search space is absolutely enormous. Here, look at what it looks like just with 2 letters and 2 letters. I let you imagine what it's going to look like with computer and information, for example. It will not even fit on the slides. So the search space is absolutely gigantic, and it would be totally unrealistic to try to compute the minimum edit distance by comprehensively or exhaustively enumerating the search space, right? Oh, this is an example of one of the possible chains of edits, right? So you remove R, you add O, you remove O, you add T, and you arrive to what you want, right? Okay. So how do you do if you wanted to? Like, let's say brute force, right? Maybe we have a supercomputer and we can do a brute force approach. So there are 2 ways that you should have learned in the algorithms and data structure. There is the depth first search, where you visit the tree going all the way down, then up again, then down, and so on. So you go like this. And there is the breadth first search, where you just keep in a queue the to-dos, but you still go level by level. Who is familiar with this? Right, most of you. Okay, very good. So you have the choice between this and this, but as you can imagine, it's just going to be incredibly costly. And this one costs even more memory because you need to keep track of the to-dos. So how do we do better than that? Well, we could be clever and notice something. It's repetitions. For example, you see that T going from the empty words to T appears multiple times. I put it in yellow everywhere, right? Then you have O from O to nothing. I put it in blue and so on and so on. These, in fact, are equivalence classes, right? You could consider that two of the nodes in that tree are in equivalence classes. You color them in the same way. And so what do we do when we have an equivalence relation, like you probably see in discrete mathematics? When you have an equivalence relation, you quotient your set with this equivalent relation, and then you no longer consider the individual elements, you only consider the equivalence classes, the bags, right? For example, if you quotient the set of all integers z, you quotient it with modulo 2, right, z over 2z, then you have one class with all the odd integers, one class with the even integers, but then you forget about these individual integers. You just have two classes. You have 0 and you have 1, but the class of 0 and the class of 1, right? So this is quotienting. So let's quotient. We can do it not just with integers, but also with nodes here. So what happens if we quotient that? This is what we get, right? Oh, that starts looking like something that's no longer exponential. That's in fact polynomial, quadratic, right? So this actually looks good. Right? So of course, the reason why I can do this has to do with the fact that these edges that you see here are independent of the specific choice of item in the class. It's only depending on the class, right? That's the reason why, for example, if you do modulo 2, 1 plus 1 gives you 0, right? Modulo 2. Why does that work? It's because if you take any odd integer and any other odd integer, like 7 and 9, for example, and you add them, 16, you always get an even integer. So plus is said to be compatible with this quotient, right? And in that case, the edges of the graph are in fact compatible with our equivalence relation, which is why we can actually take the quotient of the graph and turn it maybe 45-degree rotation, thank you, and there you go. This is called dynamic programming. Who heard of dynamic programming? You did, right? So that's exactly what it does. A dynamic programming, it's just a technique that takes the quotient of the search space in order to obtain something polynomial, and then you can iterate polynomially in the search space, but now you can do it for every single item in the quotient set of the search space, right? So I don't know if this is how it was explained, dynamic programming, but that's how I like to explain it, right? It's a quotient of the search space. Okay, awesome. So now that we know that this is dynamic programming, we can just take the two words and directly try to work on the quotients of the search space instead of the search space itself. And now let's say two more complicated words, because now we have a simpler way. We can go to 3 and 3. So let's take cat from CAT to 8, ATE, right? And this sharp here is just for the empty word, right? So let me give you an example of what we have here. This cell right there, for example, would be the distance. We want there to be the distance between CA and AT, right? Here, that would be the distance between cat and just A, right? Here, it's the distance between CA and the empty world, right? So every one of the numbers that I want to put in here via dynamic programming will give me the distance between two prefixes of the two words, right? I already put an obvious one in place, which is 0, because if we go from empty to empty, how many edits do I need at least? Well, 0, right? So this is why I put the 0 in there. And now, as is typically done in dynamic programming, we are just going to iterate our way through the table. So we could go line by line and then column by column in every line, or we could go column by column and then within a column line by line, or we can go diagonally. That depends on the specific of the dynamic programming algorithm. But basically, we want to go from the left to the right and top down, right? So here, let me do an easy part as well, right? So if I want to go from empty to A, then it's 1 edit. I just add A. If I want to go from empty to 8, then that's 3. I add A, I add T, and I add E. If I want to go from CA to the empty world, then that's 2, right? Because I remove C and I remove A, and so on and so on. For whom is that clear? Right, that's the easy part, right? These are just the boundaries of our dynamic program. And now we are going to complete recursively the cells. So every cell is going to depend on the cell above it, the cell on the left, and the cell on the top left. And in order to understand, this is actually quite natural to understand. For example, if you know how to go from C to the empty world, and you know the edit distance for this, then in order to infer the edit distance from that same word here, but with one more letter, it's basically whatever number is here, plus 1. And the plus 1 corresponds to adding this letter, to adding this letter, right? You go from C to nothing in a step of 1. So you go from C to A by first going to nothing, and then plus 1 by adding the letter A. First possibility. Second possibility, you know how to go from the empty world to A, right? And you have whatever number of steps. Then you have one more step to actually remove C, right? So you know how to go from C to A by removing C, and then you're back to the problem of the empty world to A. So this is this number here, plus 1. And the third possibility is you know how to go from the empty world to the empty world, and then you have one extra step, which is replacing C with A, or substituting A for C. This is the one I never remember in English. That's I hope I got it right. So you substitute A for C, you put A instead of C. That's one step, right? Replacing a letter with another is one step. So I take this plus 1, right? Is it always plus 1 here, substituting a letter for a letter? In general, here it's A and C, right? But in general, is it always going to be 1? Yes? Exactly. If the letters are the same, this is going to be 0, right? Then you don't substitute anything. All right. And then you take the mean, right? You look at all the possibilities, the 3 possibilities, and you look at the mean. So here we have 2 if we came from the left, 2 if we came from the top, and 1 if we came from the top left. The minimum is 1, so we just put 1. And now we do it for every cell like this. So here it's the minimum of 1 plus 1, 1 plus 1, and 2 plus 1. So that's 2. Here is the minimum of 2 plus 1, 2 plus 1, and 3 plus 1. So that's 3. And now this is basically what you've just mentioned, and this is correct. Here, look, we have A and A, right? So here, if I go from C to the empty world and I do it in one step, then going from CA to A is the same number of steps as here, because A is just, it's already there, right? So here that gives me 1. Here is the same, 1 plus 1 and 2 plus 1. So the minimum is going to be just 1, right? And then I just go ahead. Here it's 2, here it's 3. You can do it offline if you want, but that gives me my table. And my final result is here at the bottom right. And that took quadratic time, right? Just compute it, all of each one of the numbers of the table. So the complexity of the algorithm is the spatial footprint of the structure, which is the rectangle, quadratic. What's more, I can add one more bell and whistle to the algorithm that I not only computes the numbers, but I also add back pointers. So at every step of the way, I keep track of where the minimum was, right? So for example, I know every step of the way backtracking from there. Sorry, my arm is not long enough. So here I just remembered that these 2 actually came from here, and then you just navigate your way back, and you can even reconstruct the entire path that is optimal, right? So all you need is a slight augmentation of the algorithmic procedure to add these back pointers, and then you know how to find your way back there. All right. For whom is that clear? Who would be able to do that on any pair of words? Okay, very good. All right. So this is the edit distance, or the Levenstein distance. It's really a textbook thing. You have to know this one, not just for information retrieval, but for many other applications. Can also be useful, you know, if you are working in a company and you suddenly need to compute an edit, like for example, for diff algorithms. How do you write a diff program? Well, a diff program works using this. This is the secret to compute a diff, right? Okay. Now, here's the problem. We know how to compute the edit distance between a word and another word. So in essence, if I have a query and I would like to correct it or find the mistakes in the query, then what do I need to do? I need to compute the edit distance with every single term that I have in my index, and then take the minimum edit distances, right? So it's a minimum of the minimum here. It's really a second level. So I need to find the shortest distance, the shortest term. So computer is not in my index. What is the shorter one? Well, here we know with a distance of 1, just adding O, we will find computer, right? But in general, the way you find it is to compute all the edit distances. Is that reasonable? Not really, right? Because now you have to compute, in that case, you have 500,000 terms. You cannot compute 500,000 times the edit distance, right? That wouldn't be quite reasonable. It would still be better than the exponential way, but still not optimal. So in practice, this is not how this is done, at least for spell checking. What we can do instead, there are several flavors of that, of course, and in practice, there's different solutions, but one way could be to pre-select a few terms. You don't compute the edit distance with every single term that you have in your index, but you just select a few ones. How do we do that? Well, there is a trick going back to the k-grams. Remember, the k-grams is what we've just seen half an hour ago. So let's come back to the k-grams. Can we have this concept of distance between two words based on the k-grams? The answer is yes, because intuitively, this is an intuition. Two terms that are close to each other, they will have many k-grams in common. Do you agree with this? Computer and computer, they will have many k-grams in common. So this, if you look at the Venn diagram of the k-grams, then they will be like this, and this would be words that are further apart. They will not have a lot of k-grams in common. Here's an example: computer and computer with a missing O. So you see in the middle, we have all the k-grams that belong, the 3 grams in that case, that belongs to both. So MPU, PUT, ER dollar, do not forget the dollar, UTE, TER. Now $CO, COM, and OMP, they only are in computer, but not in the misspelled word. And $CM and CMP are only in the misspelled word. For whom is that clear? All right. So now you could just count whatever is in the intersection, so the number of k-grams that they have in common, and then you look for the ones that are very, very large, right? Can you just do that? Is that a good idea? In fact, not really. So here's another example where you have a very small distance. The problem, as we will see, if you just count the number in the intersection, what you're missing is a renormalization factor, because you don't consider that the words might be very, very long or very, very short, right? So you could have two words that are close to each other and that are very short, but since they are very short, the number of k-grams, the absolute numbers, is going to be small. Or you could have words that are very, 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 very long, like, I don't know, supercalifragilisticexpialidocious or something like that, like super long words. And then by accident, you just have plenty of k-grams in common, even though the two words have nothing to do with each other, right? So we will need some kind of renormalization factor, right? But the good news is we have this index. Remember, this is an index we've already built in the context of wildcard queries. So that's the k-gram index, and we can actually use that index. So for example, computer, here, we can look for the k-grams that they are in there. So these are the k-grams on my misspelled word, and then I look up each one of the k-grams, and then I find here the number, the words that appear the most often in there. So it seems to be computer in that case, because it's 1, 2, 3, 4, 5 times, right? 5 occurrences, right? So computer has 5 3 grams in common. Terran has one only, TER. Right? So if you have to choose between computer and Terran, then you will put computer, right? But again, here we are just counting in absolute numbers, and that's not good, right? Because in that case, here's an example. Here we selected computer on the basis of 5 k-grams in common. Here's an example with board and boardroom. They have 3 2 grams, bigrams in common, right? in order to renormalize, because 3 might be a lot if the words were short, but here 3 is not a lot because there's a lot of bigrams outside of the intersection. So we need to renormalize. How do we do the renormalization? We just divide by the total size, right? So what we do is we do not just count the number of k-grams in the intersection, we renormalize and divide by the total number of k-grams in the union. So it's the cardinality of the intersection times the cardinality of the union. So in that case, the answer already popped up, but what is the what would be the what do I compute here? It's called the Jacquard coefficient. What do I get? Then you earn your break. Yes? Anybody? Yes? 1/4, 3 in the intersection, divided by 12 in total. So now you've earned your break. So I'll see you in 15 minutes for the continuation of the lecture. Thank you.